Welcome to the Unit 7 Section 1 video on exponent rules. A monomial is a number, a variable, or a product of numbers and variables with whole number exponents. So here's some examples of some monomials. You can have just a number, such as -9. You can have just a variable, such as y. You can have a combination of a number and variable, where we have a coefficient and a variable, like 7a. You can also have a variable with a power attached to it or an exponent attached to it. So 3y to the third would also be a monomial. And you can have even a fraction as your coefficient. So 1/2 abc to the fifth. We have multiple variables in here, but they're all being multiplied together. So all of these are monomials. These are examples of things that are not monomials. Square root of x is not a monomial because you cannot have a square root on a term and it be considered a monomial. You cannot have a variable in the denominator, so x over y would not be considered a monomial. Now, if it was a variable over a number, that would be okay. X over 2 is the same as 1/2 x, right? So that would be considered a monomial, but as long as you have a variable in the denominator, it's not a monomial. We also have 3 minus 4ab. This would not be considered a monomial because it is not one term. Remember, every time you have a plus or a minus, that separates terms. And so here we have two terms, so therefore it is not a monomial. Here's another example where we have the variable in the denominator. It is not a monomial. And then if you have a negative exponent, you cannot consider it a monomial. So x to the -2 would not be considered a monomial, and the reason being is because if you were to rewrite it, you would have x squared in the denominator. And we're going to talk a little bit more about that later on. So let's take a look at this example and identify each of the following and whether or not they are monomials. So 4x squared. Well, we have a coefficient, we have a variable, and we have an exponent. So this is a monomial. 5 over x. X is in the denominator, so this is not a monomial. 5xy to the third. We're all multiplying. Everything's in the numerator. We have a coefficient, we have an exponent, but there's nothing in the denominator in terms of variables, so this is a monomial. -7, a squared b to the fourth. Again, a coefficient, a couple of variables with a couple of exponents. This is a monomial. Square root of xy, can't have a square root, so it's not a monomial. And then 1/3 a to the fifth. 1/3 is a coefficient. It's okay to have a fraction as long as it's a numerical fraction. And then we have a to the fifth, so that would be a monomial. Many monomials consist of a base, exponent, and coefficient. You've already seen that a bit in the previous example. So the base is the number or variable being raised to an exponent. The exponent is the number that indicates how many times the base in a power is used as a factor. So for example, we have x squared, so that is the same as x times x. And the coefficient is the number that is multiplied by the variable. It sits out in front. So now let's identify the base, exponent, and coefficient of the following terms. So for this first one, our base is the item that is being raised to a power, so that would be our y. Our exponent is the power, so that is 3. And our coefficient is -7, the number out in front. If there is a negative in front of your coefficient, you must include the negative sign as part of your coefficient. That goes for subtraction. If you have different terms, your subtraction is making that term negative. 14x to the fifth, our base is x, our exponent is 5, and our coefficient is 14. X to the 12th, our base is x, our coefficient, or I should say our exponent, is 12, Now our coefficient, there's no number out in front of the x, so when there's no number out in front of the x, it is understood to be 1, because we do not need to write 1 times x to the 12th. We can just write x to the 12th. So no coefficient is actually a coefficient of 1. And then negative a to the negative 7th, our base is a, our exponent is negative 7, and our coefficient is negative 1. Now notice d here does have a base, an exponent, and a coefficient, but it is not a monomial because it has a negative exponent. Remember, negative exponents mean you do not have a monomial. Like terms are terms that contain the same variables with corresponding variables raised to the same power. So they have to have the same base with the same exponent. The coefficients, however, can be different. So let's list the like terms in each set. We have 5x squared, 6xy, 4x, 5y, and 7xy. Well, if we look at the first term, 5x squared, there's no other x squared term, so we can throw that out. On our second term, we have 6xy. We also have 7xy, so those would be like terms. And then we have a 4x, but no other x terms, and 5y and no other y terms. So those would be the only like terms, 6xy and 7xy. For b, we'll go through the same process, and we are going to look at the first term first. So negative 2xy squared. Do we have any other terms that have an xy squared? And if we look, we notice that we have 7xy squared. So those would be like terms. If we go to our second term, there's no other xy terms. We go to the third term, there's no other x squared y terms, and there's no other x terms for that fifth term. So those are our only two like terms. For c, we have 7ab. If we go down the list, we have a negative ab. So those would be like terms. Now let's go to our second term. We have negative 3a. If we go down our list, we also have a negative 14a. So those would be like terms. And if we have 8b, there's no other b terms, and we have an ab squared, and there's nothing like that. So those are our two sets of like terms. One thing that I would probably do, and this may help you out, is as you list your like terms, scratch them off your list so you have a better view of what you have left to look at. For d here, we have 7x. If we look down our list, we have a negative x, so those are like terms. And then we have a 9xy and an 8xy, so those are like terms. A power can be expanded by multiplying the base by itself the number of times indicated by the exponent. Conversely, a number or variable multiplied by itself can be collected into an exponent. So for example, if we have 5 times 5 times 5 times 5, that can be rewritten as 5 to the 4th because we are multiplying 5 4 times on itself. We have x times x times x, so we can rewrite that as x to the 3rd, and y times y can be rewritten as y squared. So we're going to write the following using exponents. 4 times 4 times 4 times 4 times 4. We're multiplying 4 5 times on itself, so we can rewrite that as 4 to the 5th. Here, we're multiplying x 4 times on itself, so we can rewrite that as x to the 4th. Now, we're going to go the other way. We're going to write the following without using exponents. So for this first one, 5 to the 3rd, x squared, y to the 4th, you're going to write out 5 3 times multiplied, x 2 times multiplied, and y 4 times multiplied. Now for b here, this one gets a little trickier because we have a negative 4 squared out in front. Now, because there's no parentheses around the negative 4, that square only affects the 4. So you're going to have a negative out in front, and then 4 times 4 before you do your 4 x's and your 1y. Okay, so remember, the only way we would have negative 4 times negative 4 is if we were to have a parentheses around the entire negative 4, because then the square would impact the entire thing. But because the square is only on the 4 itself and not on the negative, you're only going to multiply the 4 times 4. You will just stick your negative out in front of the entire thing. Now let's talk about the product rule. Recall that an expression of the form x to the n is a power. The base is x and the exponent is n. So here's a table of powers of 2 that we're going to use for reference as we investigate the product rule. So let's take a look at 3 different multiplication problems here. We have 4 times 16 equals 64, 8 times 16 equals 128, and 8 times 32 equals 256. So you'll notice that all of these numbers in these problems are powers of 2. If you look at your table, you can see 4 is there, 16 is there, 64, 128, 32, 256. They're all up in that table. So we can rewrite these pieces as powers of 2. So let's do that with the first one. 4 is 2 squared, 16 is 2 to the 4th, and 64 is 2 to the 6th. We can do that with the second one as well. 2 to the 3rd times 2 to the 4th equals 2 to the 7th, and 2 to the 3rd times 2 to the 5th equals 2 to the 8th. I just went up to my table here, found which power of 2 goes with each number, and substituted that power of 2 in for the number. Now let's look for a pattern in the exponents. So if you look at the exponents, you have 2, 4, and 6. Okay? And we know that 2 plus 4 equals 6. So there is a true statement. Let's see if the same holds true for the second one. We have a 3, a 4, and a 7. Well, 3 plus 4 does equal 7. And then if we look at the last one, 3 plus 5 does equal 8. So we have found that we can multiply powers that have the same base by adding exponents. So that brings us to the product rule. For any number a and all integers m and n, a to the m times a to the n equals a to the m plus n. You can combine your 2 pieces that you're multiplying by adding the exponents. So let's use that in an example. Here we have 2n times 3n. First, you're going to split up your coefficients, and you're going to split up your variables. Pull your like variables together. So here we have 2 times 3 and n times n. Because remember, when you have 2 times n, a coefficient and a variable, we're multiplying. And so we're doing 2 times n times 3 times n. And if you remember, we have previously talked about the fact that we can multiply things in any order that we like, and it doesn't change the outcome. So here, we're multiplying our coefficients first, and then our variables. So if we do 2 times 3, that's going to give us 6. And then if we do n times n, that has the same base. And if there's no power, it's understood to be 1. So we can do n to the first times n to the first as n to the first, or n to the 1 plus 1. Okay? And if we add those 2 powers together, we get squared. So 6n squared. And it makes sense, right? N times n should give you n squared, just as 2 times 2 gives you 2 squared. All right, for b, let's take a look at this one. Again, let's separate our coefficients and our variables. 4 times 2 is going to give us 8. We are going to use the product rule to do x squared times x cubed. So we take our 2 and our 3 and we add them into a power of x. And then we get x to the 5th when we do 2 plus 3. So our final answer is x, or 8x to the 5th. For C, we have 2xy to the third times 2x to the third y to the fourth. So again, we are going to separate our coefficients and our variables, putting our x's together and our y's together. 2 times 2 gives us 4. X times x to the third gives us x to the 1 plus 3. X to the third times x to the fourth gives us, or I should say y to the third times y to the fourth gives us y to the 3 plus 4. Then we go to 4x to the fourth, y to the seventh when we add our exponents. And then for D, we have 2a squared b squared times a times 2a to the third b to the fourth. So separate out your coefficients, separate out your a variables, and separate out your b variables. 2 times 2 gives us 4. We're going to add all of our exponents in our a. We're going to add all of our exponents in our b using the product rule. And when we add our exponents, we end up with 4a to the sixth, b to the sixth. Now let's move on to the quotient rule. Again, we are going to use a table of powers here to assist us in investigating the quotient rule. So here we have powers of 3. 3 to the first, 3 to the second, 3 to the third, 3 to the fourth, and 3 to the fifth, and the values for all of those. So let's look at 3 examples here. I have 81 over 27, which equals 3, or I can say 81 divided by 27, which equals 3. 27 divided by 3 equals 9. 243 divided by 9 equals 27. So let's rewrite all 3 of these using our powers of 3. We do that for the first, the second, and the third. And let's see if we can find any pattern in the exponents. So on the first one, we have 4 and 3 equals 1. What operation do we need to do to have 4 blank 3 equals 1? Well, we could do subtraction. 4 minus 3 equals 1. Let's see if it works for the second one. 3 minus 1 does equal 2. 5 minus 2 equals 3. So you can divide powers that have the same base by subtracting the exponents. And that brings us to the quotient rule. For all integers m and n, and any non-zero number a to the m over a to the n equals a to the m minus n. And it almost makes sense, right? We had the product rule that used addition in the exponents. So when we're multiplying, we add the exponents. Here, when we're dividing, we subtract the exponents. Multiplication goes with addition. Division goes with subtraction. So let's simplify b to the fifth divided by b squared. So I'm going to show you 2 ways. First, let's use the quotient rule. We're going to subtract your exponents. So you'll do b to the 5 minus 2, and that will give us b to the third. Well, let's look at it by expanding our powers. So we have b to the fifth, which is 5b's multiplied on itself, over b squared, which is 2b's multiplied on itself. Well, we can cancel 2b's from the top and the bottom, which leaves us with 3b's multiplied on itself, which is b to the third. So it does work. So now let's look at a little bit more involved example. Here we have 2 variables with exponents. So, like we did with the product rule, we are going to separate out our variables, put a's together and b's together. Here I give you a little reminder that a by itself on the denominator is a to the first. We will subtract our exponents on each variable, and that will give us the answer a to the third b. Now you may be wondering, why are we doing all of this? Why are we learning all these rules? Well, a to the third times b is much easier to work with in the context of a much larger problem than what we started with, the a to the fourth, b to the third, all divided by ab squared. A to the third times b is much simpler to carry forward if there was another part of this problem. So this is why we are learning these rules, and this is why we're learning to simplify. Simplifying things will make your life easier. Next, we have power of a power. Let's take a look at 5 squared raised to the 4th. We can rewrite that as 5 squared times 5 squared times 5 squared times 5 squared. If we were to do that, then we can use the product rule to add our exponents, since we have the same base of 5. So this would be 5 to the 2 plus 2 plus 2 plus 2, which would give us 5 to the 8th. Similarly, if we have x to the 6th squared, we can rewrite that as x to the 6th times x to the 6th. We can again use the product rule to add our exponents and then get our final answer of x to the 12th. Well, looking at these two examples, let's see if we can find a pattern. Looking at the exponents once again. So we have 2 blank 4 equals 8. Well, 2 plus 4 is not 8. 2 minus 4 is not 8. But 2 times 4 is 8. And let's see if it works for the second one. 6 times 2 is 12. So you can find the power of a power by multiplying the exponents. And that is the power of a power rule. For any number a and all integers, m and n, a to the m raised to the n is a to the mn. We just multiply our exponents when we take power to a power. So let's simplify each expression. X to the 12th squared. So what we do is we multiply our powers, and we get x to the 24th. For this one, we have x squared over 5 raised to the 4th power. Now, that 4th power is going to act on both the numerator and the denominator because it's acting on everything inside the parentheses. So you're going to do x squared times 4. Okay, x to the 2 times 4. We take power to a power and multiply our powers. And then we take 5 to the 4th on the bottom, which is going to give us x to the 8th over 625. For c, again, we've got 3x squared all to the 4th power. That 4th power operates on everything in the parentheses. It operates on the 3, and it operates on the x squared. So we have to take 3 to the 4th, and we have to take x squared to the 4th by multiplying our powers. And 3 to the 4th is going to give us 81, and x to the 2 times 4 gives us 8, x to the 8th. Again, for d, that 5th power is operating on everything inside the parentheses. And we're going to use the power to a power rule for all 3 pieces inside the parentheses. So we'll do a to the 3 times 5, b to the 6 times 5, and c to the 2 times 5. When we multiply all those powers, we get a to the 15th, b to the 30th, c to the 10th. And yes, that is a monomial because it is all one term. We have variables raised to exponents, but it is a monomial. Now let's take a look at the zero exponent rule. There are 2 ways to simplify a to the 3rd divided by a to the 3rd, where a is not 0. Of course, a cannot be 0 because we cannot divide by 0. So let's take a look at the first way. I can rewrite a to the 3rd as a times a times a on both the top and the bottom. When you do that, everything cancels and we're left with 1. The other way to look at this is through the quotient rule. We do a to the 3 minus 3, which gives us a to the 0. Well, since we have a to the 3rd over a to the 3rd equaling 1, and a to the 3rd over a to the 3rd equaling a to the 0, we can conclude that a to the 0 equals 1. In general, any non-zero number raised to the power of 0 is equal to 1. And that is the zero exponent rule. For any non-zero number a to the 0 equals 1. So in example 10, we are going to simplify. Well, everything inside the parentheses is taken to the 0 power. So since everything in the parentheses is being taken to the 0 power, it equals 1. In the next example, again, we have a lot of stuff inside the parentheses. We could do quotient rule and simplify what's inside the parentheses, but there's no need because everything is taken to the 0 power. It's simply going to be 1. It doesn't matter how complicated what's in the parentheses is, as long as it's non-zero and it's taken to the 0 power, it's going to be 1. This brings us to the negative exponent. There are two ways to simplify k squared divided by k to the 7th, where k is not 0. So first, let's take a look at it in terms of how many times we're multiplying k on itself. 2 times in the top, 7 times in the bottom. You cancel out 2 k's off the top and 2 off the bottom. You're left with 1 over 5 k's multiplied on itself, which is 1 over k to the 5th. Now let's take a look at it using the quotient rule. We can subtract our exponents, and we get k to the negative 5th, which is a negative exponent. Since we have k squared over k to the 7th equaling 1 over k to the 5th, and also equaling k to the negative 5, we can conclude that 1 over k to the 5th equals k to the negative 5. This suggests the following definition, which is that of the negative exponent. For any non-zero number a and any integer n, a to the negative n equals 1 over a to the n. So basically, your negative exponent, if it's in the numerator, you're going to move it to the denominator and make it positive. If your negative exponent is in the denominator, you're going to move it to the numerator and make it positive. So let's simplify 12x to the negative 3. So we can move our x to the negative 3 that's in the numerator down to the denominator, and now we have 12 over x to the 3rd. It is considered simplified because we do not have any negative exponents. You do not want any of your answers to have negative exponents in them. Let's simplify 4 over x to the negative 2. Well, since that negative exponent is in the denominator, to make it positive, we're going to move it to the numerator, which would make it 4x squared. The x moves up to the top. We take the negative off of our exponent, and it becomes 4x squared. Let's do one that's a little bit more involved. So for this one, we are going to have to first use the quotient rule. So let's split up our pieces. Let's start with our coefficients. Then we're going to put our r's together, our s's together, and we'll put our t term by itself. So negative 6 over 18 simplifies to 1/3, negative 1/3. We can use the quotient rule to do r to the 3 minus negative 7. We can use the quotient rule to do s to the 5 minus 5. And we can use the negative exponent rule to bring our t to the negative 2 up to the top and make it t squared. Now let's use our quotient rule to go ahead and subtract our exponents. So 3 minus negative 7 gives us 3 plus 7, which is r to the 10th. S to the 5 minus 5 gives us s to the 0. And then we can use our 0 exponent to make s to the 0 1, so that term goes away. I'll collect my r to the 10th and t squared into the top, and the 3 will sit in the bottom. And so our final answer is negative r to the 10th t squared all over 3.
Thanks for checking out my video in the Foundations in Algebra series. You can subscribe to my channel. I've got the next video queued up for you, and if you need to check out any of the videos in the course, I've got the course playlist for you here as well. Thanks for watching.